Hi, in this video, we're going to look at an extension of logistic regression to the case of multiple classes, which is often referred to as multinomial logistic regression. And to do so, we'll introduce the Softmax function. Okay, so just a really quick recap of logistic regression. We saw it in the last 3 videos. And the basic idea here in logistic regression is that we'd like to, we have 2 classes, +1 and -1, and we'd like to train a linear model to predict the probability of a given training example with a feature vector x lying in class 1. And the way we made predictions was that we, during training, we find this vector w of parameters, and given a feature vector x, we compute the inner product and apply the sigmoid function, resulting in this value here, which lies between 0 and 1. Okay. And of course, the intention is that we would like this prediction to equal the probability that the label is 1 given the feature vector x. Okay. And so basically we're learning this probability distribution, right? We're learning what is the probability that the label is 1. And since there are only 2 classes, this also tells us what is the probability that the label is -1. Good. So we also looked at this in the supervised learning setup. The unknown target function is now an unknown target distribution, right? For every single feature vector, there's distribution over labels, and this is really what we're trying to learn. We're trying to learn this unknown target distribution. And again, what we have available is training examples x1 to xn, drawn independently from some unknown input distribution d. And then for each of these feature vectors x1 to xn, we draw the label yi from the conditional distribution on the labels given the feature vector xi. The learning algorithm is then supposed to output a hypothesis such that if I evaluate the hypothesis on a new example x drawn from this unknown input distribution d, then h of x should hopefully be close to the probability that the label is 1. Okay, so basically we're trying to learn the distribution of the label given the feature vector x. Okay, and the way we did it was we used this likelihood. Just again, a really quick recap. So the intention is that given the hypothesis of the model parameters w, we would like that this sigmoid of the inner product between w and x should equal the probability that the label is 1. So which means that if we actually assume that this was the case, that actually was perfectly equal to the probability that the label is 1, then we could compute the likelihood of the data labels for this w. So this is basically the probability that we would actually see these labels y1 to yn given the feature vectors and the choice of parameters w. And this would just be the product, because the samples are drawn independently, just be the product over all the training examples of the probability of seeing the label yi, and we computed in previous videos that this would be the probability. Okay. And the way we could maximize this likelihood, right, we'd like to choose the w that maximizes this probability. The way we did it was that we instead minimized the negative log likelihood, which would get rid of the product, and also turn this function that we're trying to minimize into a convex function. And then we computed the gradient of this convex function, and we use gradient descent to minimize it, to minimize the function. Okay, so those were the steps that we went through in the last 3 videos. So in this video, we'll introduce what's called multinomial regression, or multinomial logistic regression. So the solution that we saw last time, just vanilla logistic regression, we assumed that there are only 2 classes, -1 and +1. And the question is just what happens if we have k classes instead. For instance, we're predicting whether a wine is a red wine, white wine, or rosé, right? So there are multiple different classes that we have to output one of them. And what we would like to do is, in general, we can think of it as there's a probability of being in each of the 3, or in general, each of the k classes. And we would like to learn the probabilities of each of the k classes, right? So we want to learn a whole probability distribution over classes. Okay. So to do so, I guess the first question to ask is, now that we have k different classes instead of just 2, in 2 classes, we just use -1 and +1 to represent the class. So how should we represent 1 among k different classes? Okay. So I guess the first thing that would come to mind, the most natural thing, is to just say, well, I just pick an integer for each of these k classes. You know, say red wine is class 1, white wine is class 2, and rosé is class 3. And you know, maybe you just have to predict which of these numbers or which of these classes that the wine corresponds to. The problem is that if you imagine having all these numbers assigned to the different classes, then somehow, it seems like there's some ordering on the labels, right? Because the numbers 1 and 2 are really closer to each other than 1 and k. In particular, you could imagine that if your machine learning model is outputting a number that's supposed to be close to one of these k integers, then small mistakes would make it more likely to, end up in a class that's close by in the assigned number. And maybe in many applications, right, there's no notion of one class being closer to the other, right? So maybe they're just arbitrarily, there's no similarity between the classes. So if we just assign 1 to k as numbers, then 1 and 2 would somehow be closer to each other than 1 and k. So this is not really the way that we're going to do it. Instead, we're going to introduce what's called the 1 and k encoding. Okay, and the idea here is that instead of labels just being a number, they're going to be vectors. Okay, so in particular, if we have k classes, then we're going to represent each of these different classes using a k-dimensional vector. And what we'll have is that this k-dimensional vector is going to have one coordinate for each of the k classes. And we have a really simple representation of each of the labels, right? So if the label is the ith of the k different labels, then the vector representation of this label is just a 1 in the ith coordinate and 0 everywhere else, right? So we kind of just use the standard unit vectors to represent our labels. Right, so for instance, here with the example with the wine, the 3 different classes, so we represent each class as the 3-dimensional vector. And you can see here that the red wine, or the label red, would have a 1 in the first coordinate and 0 everywhere else. White would have a 1 in the second coordinate and 0 everywhere else, and rosé would have a 1 in the last coordinate and 0 everywhere else. Okay, so now they each have their own coordinate when we're representing these labels as vectors. Okay. So this is the 1 and k encoding that we're going to be using. Now, again, if we want to say, so if we had 2 classes, right, we represented the input data really as a matrix X that had the feature vectors as rows, and a vector Y that had the labels as entries. It's a column vector here. And each of these entries in the column vector was -1 or 1, corresponding to the 2 classes. Now, instead, if we go to the k classes, the data matrix X is still the same, but the labels now is a matrix. It still has 1 row for each of the data items, but now instead of having just a single column, meaning that it's a vector, now we're going to have k different columns, 1 for each of the classes, right? So every row of this matrix corresponds to the label of a data item, and it has k different columns. Basically, we're going to use this representation that we said before, right? So each of the rows of this data matrix that corresponds to the label of a single training example. Therefore, if we use this 1 and k encoding, each of these rows is going to have a single 1 in the column corresponding to the actual label of that element, and the remaining columns are going to be zeros, right? So this is going to be a matrix with a single 1 in every row. Good. So this is the difference in the representation. And now for logistic regression with 2 classes, right, the way that we made predictions was that we evaluated the sigmoid function on the inner product between W and the feature vector X, right? This gave us a number, and the intention was that this should equal the probability of seeing the label 1 given this feature vector X. And of course, right, if we know or we can learn the probability that the label is 1, when there are only 2 classes, this also learns the probability that the label is -1. Right, because you can just subtract the probability that it's 1 from 1. Now, for k classes, what we're really interested in, we're not interested in learning just 1 probability, but we're actually interested in learning k different probabilities, right? We want to learn for every single class, what is the probability that the label is equal to this class, given the feature vector X. And so we have a whole set of k different probabilities we want to learn. So we want to learn the whole distribution on the label given the feature vector X, right? So that's the goal. Okay, so we'd like to still try and use linear models like we did for logistic regression. So we need to figure out how do we modify or extend or use the 2-class case as inspiration to come up with a way of representing these k classes and making predictions here. Right, so the first observation is that we want to output something for each class, right? We have to output a probability for each of the individual classes. Okay. And these should be probabilities, right? So which means in particular, they should sum to 1 and they should be non-negative. So what we're going to do is that we're going to, instead of using on this vector of weights that we're training in the 2-class case, what we're going to have is a whole matrix full of weights, and these are the ones that we will be searching for or learning in our learning algorithm. Okay, so this is the new setup here is that before the vector that contained all the parameters that we learned, the W, was a column vector with D entries. Now it's going to be a D by K matrix. So it's going to have a column for each of the K classes. Okay, so this is the new set of parameters that we're introducing in the model. We want to train or figure out what should all these parameters be. And so just to try and motivate how we're going to make predictions, recall again, right, in the 2-class case, the estimates of the probabilities that we're going to output are going to be based on the inner product between X and W, right? So it was really a linear model where we compute inner products, right? We applied the sigmoid function to this and to obtain our predictions. So we'll try to do something similar, so it's still like a linear model. And for K classes, what we could do instead, it's very simple. We just base the estimates on X transpose W instead. Right, so we take the X and multiply it with the whole matrix instead of just a column vector. Now, so if we look at what is this product, right, X transpose W, then this is going to be a row vector that has K entries. Right? Before it was just a number in the binary case, but now it's going to be a row vector that has K entries. Now, the ith entry is just going to be the inner product between the ith column of W and X. Right, so or the general, okay, so the jth entry is the inner product between the jth column of the weight matrix and X. Now, one can think of this, right, as really what we're doing here is that we can think of each of the columns of W as a separate linear model. Right, basically we have one linear model for each of the classes. And so all these linear models, so basically we kind of, in some sense, we evaluate all these linear models on the feature vector X. Each of them outputs a number based on the inner product between this vector for this given model and X. Right, so we somehow want to base our estimates on this. We have to turn this vector somehow into a probability distribution, right? We want a probability distribution over each of the K classes. So somehow we need to find a way to turn this row vector into a distribution over the K classes. And this is where we introduce the Softmax function, which is inspired by the sigmoid. So in general, if I have a vector set of K entries, then we define the softmax of set is a new vector that has probabilities. So all the entries lies between 0 and 1, and they sum to 1. So softmax of set is a function that I can apply to a vector. And the function is just defined like this. So what you do is you can look at what is the jth entry of softmax of set. What you take here is the jth entry in set, so that's the set j, and you take e and raise it to that number, okay? And now you also have a denominator here where you normalize by the sum over all the classes of e to the set I, so all the entries of the vector, and take e to the set I. So basically one should think of the denominator here as a normalization sum such that everything sums to 1. And also it's worth observing that regardless of whether the entries in set are positive or negative, if I raise e to any number, I'm going to get a non-negative number, right? So this is all going to be non-negative numbers, and they're going to sum to 1 because I have this normalization term, right? So really, this takes any given vector and turns it into a probability distribution over the K entries. Okay, simply by raising each entry, taking e and raising it to each entry. Okay, and then just normalizing. Okay, so this is a softmax. So maybe it's worth just looking at examples. So let's say I have the vector 3, 2, 4. And then what does softmax of this set look like? So in the first entry, right, I have to take the first entry of set. I take e raised to that number, and then I have to normalize it by the sum of e raised to each of the individual entries, e squared, e cubed, e to the 4th. The second entry is e squared because we have a 2 in the second entry. Normalize it by the sum of e to each entry, and finally write e to the 4th divided by e to the sum of each of the individual entries here, e squared plus e cubed plus e to the 4th. And this gives a probability distribution here. You can see that the magnitude of the entries here are proportional somehow or related to the original values, right? The bigger the original values are, the larger these entries are. Okay, so that's the softmax transformation. Okay, so the normalization, right, really makes sure that this sums to 1. So this is a probability distribution. So this is what we're going to do, right? In multinomial regression, the way that we're going to make predictions is that we're going to train or find this vector, this matrix of weights W, and then we're going to compute X transpose W and apply the softmax function to it, and this is our output, right? So instead of the sigmoid function, we output the softmax of X transpose W. That's the output, and those are our estimates of the different probabilities for each of the different classes. Okay. So in general, right, if I wanted to, I guess I could also batch this together. So if I have a whole data matrix and I want to look at what is the prediction for each of the different elements in my data matrix, what I could do is before, right, if I had a single element, I had to compute X transpose W, meaning that I should think of X as a row vector and multiply with W. This is exactly what happens if I take X and multiply with W, right, because they're already placed as rows here. So if I compute XW, then each of these rows of the matrix are going to be the ones that you would have to apply softmax to. So really, if I want to output all the predictions for all the elements in this whole data matrix, I just compute X times W and apply the softmax row-wise to this matrix. And now every single row is this probability distribution corresponding to the that data item, that feature vector. Okay, so I can do this just by a matrix multiplication. Okay. So this is the whole setup for multinomial regression. Right? We have the data matrix with the feature vectors as rows. We have the labels, the true labels. We have again n rows, one for each of the data items, and the labels are 1 in K encoded, right? So there's a single one in each of these rows representing the actual label of that element. And finally, right, there's the matrix of parameters that we want to optimize or choose carefully. And this matrix again had D rows and K columns, right? So basically we could think of it as a linear model for each of the K classes. Okay. So the one up here just indicates the classes we've said before. Okay. So right now we need to figure out how do we train this matrix of parameters W. And the way we're going to do it is going to be similar to logistic regression. We're going to use the same intuition underneath, and that is that we would like to somehow define the likelihood of the training data given these model parameters W, and then we want to choose the model parameters that maximize this likelihood. Okay, so we need to figure out again a formula for what is the likelihood of seeing the data labels here, right? So we have the training data. If we believe W was the right model, what would be the likelihood of seeing these labels Y1 to Yn for these feature vectors? Right. So let's try to see if we can compute an expression for that. Right. So these are our data items. Again, these are drawn independently from the same unknown distributions. So the probability of seeing these labels given the data matrix X and the model parameters W is just going to be the product over all of these training examples of the probability of seeing the ith label given the feature vector xi and the model parameters W, right? So just by independence of the samples. So we just need to figure out now what is the probability of seeing the label yi given the feature vector xi and the model parameters W. Okay, so let's see if we can find an expression for that. So I claim now that this expression in here is nothing more than taking the feature vector yi, or the label vector yi. So recall now that each of the labels yi is a vector now. It's a vector with k entries, one for each of the classes. My claim is that I should just take this vector and compute its inner product with the softmax function applied to the feature vector xi's inner product multiplication with w. So it's not an inner product anymore, right? Because it's a full matrix, but the softmax applied to xi transpose w. Let's try to see why that's the case. So what's happening here, right? So recall again, right, that this vector yi, right, this is a 1 in k encoded vector, meaning that in the jth entry it has a 1 and 0 everywhere else, where the jth entry corresponds to the class or the label of this element. Now, the softmax again, right? This would contain a probability for each of the K classes, right? So each of the entries correspond to the probability of that class as predicted by the model parameters W. So really what this is doing, since this has just a single one, this inner product between yi and the softmax vector just extracts the probability for the actual class of the actual label that the data point has. And so this is clearly actually just gives, this inner product just picks that single entry of the softmax vector, which gives the probability of the concrete label. Okay, so all we have to do now is we need to find a way to maximize this expression here, the product over all the training examples of the inner product between the label vector yi and the softmax vector of xi transpose w. Right, so let's see how we can choose w to maximize this. Okay, you want to maximize this, and here you're just going to do the same steps as we did for logistic regression. And that is, of course, apply the negative log likelihood to get rid of the product, and the negative log likelihood, negative to turn the maximization problem into a minimization problem. Then we're going to scale by 1 over n just to make it look like the other loss functions that we've been working with, where it's an average over the training examples. So I'm just going to apply log, minus log to this whole expression here. So the product turns into a sum. We have the minus outside, and then inside here we just have the log of the inner product between yi and the softmax function on xi transpose w. Right, so that's the in-sample error that we're going to minimize, because this will maximize the likelihood of seeing the training data labels. Okay. Now, this function can actually be shown to be a convex function of the model parameters w, and we'll not do that here, but it can be shown. So, which means that if we think back to logistic regression, we can actually do gradient descent to minimize this expression, as long as we can compute the gradient of this loss function of this in-sample error, right? So we want to compute the gradient with respect to these the model parameters w. Okay, so let's see if we can do that. And actually, we're not going to do it. We're just going to say that this is what it is. So if you actually sit down and do the math, now the gradient here would be a whole matrix, right, with one entry for each of the parameters in W. Right, so entry I comma j would just be the partial derivative of the in-sample error up here with respect to wij. Okay, so that's all it is. And I'm just claiming without proof that the expression is this, right? You have the minus 1 over n still, and then the rest just turns into, after a bunch of simplifications, into x transpose, where x is the data matrix, times y minus the softmax of x times y, or x times w. Okay. So we're not going to prove it, but maybe let's just do a small sanity check to see that this makes at least sense with the shapes, right? So this gradient should have the same shape as the matrix of parameters w, right? So w is a d by k matrix, so this right-hand side should at least also be a d by k matrix. Otherwise, at least we've done something wrong. So let's just check that at least that's the case. So right, so x transpose, x is an n by d, so this is going to be a d by n. Okay, y is an n by k matrix, and softmax here. So x times w is going to be an n by k matrix, and the softmax doesn't change the shape. So you subtract off two n by k matrices, which makes sense. So this is n by k, and you multiply it with d by n, which gives a d by k matrix, which is also what it's supposed to be, the gradient is supposed to be. Okay, so at least the shapes make sense, and we're just going to trust that indeed this is a valid formula for the gradient of this loss up here. Okay, so with that, we're basically done. We can just take this template for gradient descent and plug in this gradient. So the gradient descent for multinomial regression is nothing more than initializing this matrix of model parameters W just to, for instance, as normal distributed random variables with mean 0 and variance 1. Or you can find some other way of initializing if you want. And then you just have this loop where in each of the steps, you compute the current gradient for the current choice of model parameters W. You just evaluate this whole expression here. And then you take a small step in the negative direction of the gradient, right? So eta here is the step size. Here it's the gradient, and you subtract it off, so you take a step in the opposite direction of the gradient. And as we argued in the last video, this would mean walking downhill and thus minimizing the loss. Okay. Of course, you can also turn this into the mini-batch stochastic gradient descent version of it, which is a little bit more complicated, but works better in practice. So all that this is really doing is and this is just to speed up gradient descent. So basically it says, while you have more time, right, we commute all the data randomly, and then we're going to take the data in chunks of B training examples at a time. And for each of these chunks, we have the B data elements. And then intuitively, we're just going to pretend that these were our only training examples, right? So we just look at the loss function just on those B elements, and then we just compute the gradient just for those B elements. And so we're averaging over B elements of this gradient. So this is just the matrix that has all these B elements as rows, and similarly the one in K encodings of all of the B labels as columns. And then we just take a small step in the negative direction of the gradient, right? And just to remind ourselves of some of the terminology from the previous video, each time we do this permutation, this is called a training epoch, okay? And in practice, it's often the case that you reduce the step size a little bit after every fixed number of epochs. In general, we also talked about last time that a good rule of thumb for choosing this step size could be something like 0.1. Okay, so this is really an algorithm now for multinomial regression. How do we choose these model parameters W? Okay, so let us just conclude by a few remarks on implementing this in practice. Right, so recall this softmax function is sitting inside all of this. And the softmax function for a vector z was defined such that the jth entry was e to the z j divided by the sum from 1 to k of e to the zi. Okay. Now, if you wanted to implement this, there's a couple of issues with numerical stability, right? And this is because we have these exponentials, and if these z entries are large, these could become really large numbers. And just the modern computers just don't have that high precision when you're summing really large numbers. So this is not that accurate to compute, and you might get some large rounding errors. And this is just because of the way the floating point numbers are represented on a computer. So there's a practical fix that often helps for numerical accuracy here. And this is just you would like to avoid having these super large numbers. In particular, floating point representations on modern computers has much higher accuracy for numbers between 0 and 1 that they have outside that interval. So basically what we're going to do is we're going to rewrite this expression a little bit. It's going to be the same, but it's going to give a better way of computing it if you were to implement it, right? So what we do now is that we observe, okay, so this fraction here is just the same as taking the denominator and subtracting it off in the exponent here, right? So this is just the same as e to the zj minus this log here, the log of the sum of the e to the zi's. Now, of course, right, we're still summing really large numbers inside this log, and then we're taking the log, so we'll still lose precision if we're just doing this. But we can do another trick here. So what we can do now is algorithmically, we can look at these k numbers that we're summing and then pick the largest one of them, right? Let's say this is ZA. So pick the largest one, and then what we can do is we can kind of multiply or move this e to the ZA factor outside, right? So we can move it outside the sum. And then, of course, each of the terms inside the sum has to be divided by e to the ZA, but that's just the same as subtracting ZA from each of these exponents, right? Now, again, the nice thing here is that this e to the ZA just moves outside as a ZA factor or additive term. So now we have e to the ZJ minus ZA minus the log of this sum here. And now what we've gained now is that ZA was the largest of all these numbers. So all of these exponents here are less than or equal to 0, meaning that all these summands are less than 1, right? They're all less than e to the 0. So now we're really summing small numbers, and this is where there's high accuracy on floating point numbers. So doing this transformation and computing the entries using this formula instead of the direct formula up here actually helps a lot for precision. Okay. So that's what I wanted to present on multinomial regression and using the softmax function to make predictions and output probabilities.